What's up, guys? Welcome back to another Algebra 2 instruction lesson here with Mr. Gaines as we continue our work with exponential functions. Today, we are going to focus on one method of solving exponential equations. And this is going to be one of our methods that we're going to have. Essentially, we're going to create a toolbox. This is our first tool that we're going to have to solve exponential equations. And this is called using the uniqueness property. So the uniqueness property is reliant on a very key piece of information. So for any R, S, and B variables that are all real numbers, with B being the base of an exponential expression, so it has to be greater than 0 and not equal to 1. If B to the R power is equal to B to the S power, then R must equal S. And we could probably take a look at this and visually see that, yes, this makes sense. If I'm going to have a number and take it to a power, I have that same number, it's only equal if I'm using the same power. But what this allows us to do is to go from two equivalent exponential expressions and focus on just the exponents. And we can do that in a solving process. So let's take a look at number 7. It says solve each of the following exponential equations using the uniqueness property, that property that we just talked about. So what we can do here is we see that on the left, we have, on 7a, we have a base of 3 and an exponent of 2x minus 1. And this is equal to 81. So if we were thinking about trying to solve this equation, we would commonly think of a method to get x out of the exponent. However, we can use the uniqueness property if both sides of the equation can be written as the same base. So over here on the left side, I have the base of 3. What can I turn 81 into that would have a base of 3 with some kind of exponent? If you said 3 to the 4th power, you'd be correct. 3 to the 4th power, you can see over here on the calculator, is 81. So I can rewrite this as 3 to the 2x minus 1 power equal to 3 to the 4th power. So I'm just replacing 81 with 3 to the 4th power. Now, because of the uniqueness property, again, that we just talked about, when I have two bases that are equal, and their exponents must be equal. So that means that 2x minus 1 must equal 4. And from here, we can solve. We can add 1 to both sides. So 2x equals 5. Then divide by 2. So x equals 5 halves, or 2.5. And I can check this. So I can go back to my graphing calculator and take 3 to the 2 times 5 over 2 power, 5 over 2 minus 1 power, and see that this is 81. So the uniqueness property works when we are able to rewrite bases or rewrite expressions so that they are the same base with some kind of exponent. Let's take a look at problem B. So in B, I have variables in each of the two exponents. And the bases, again, are different here. So what I may be thinking about, if I see the base on the left as 25, I may try to figure out if there's a way that I can write 125 as a power of 25. Well, 25 squared is greater than 125, and so there's not any integer number that we're going to be able to use. Yes, we could work with some fractions, but let's just focus on trying to use integers right now. What I may notice is that actually 25 is the square of 5. So 5 squared is 25. So I could rewrite this as 5 squared, that's 25, to the negative 2x power. How that's helpful is that 5 cubed is 125. So I could rewrite the other side as 5 cubed to the x plus 7 power. Well, how does this simplify? Remember our exponent properties here. If I'm taking an exponent to a power, I would multiply those. So this would be 5 to the negative 4x power equal to 5 to the 3x times 21 power. Remember, I do have to essentially distribute that 3 to the x plus 7. And now I have an expression where the bases are equal. Thus, we know their exponents must be equal. So negative 4x is equal to 3x plus 21. In this case, I could subtract 3x from both sides here, and then divide by 3 to get that x is equal to -3. So let's check this. On the left side of the equation, this would be 25 to the -3 times -2, which would be 25 to the 6th power, which is a rather large number. And then let's check 125 to the -3, sorry, this would be 125 to the -3 plus 7 would be 4th power. And we can see that both of those numbers are the same. 244,140,625. So -3 would be a value for x that satisfies this equation. Let's take a look at a couple more examples here. So in problem C, now I have a fraction, 1/6, and there's many different ways that we can go about this. So in C, what I could do here is, I see that I have a negative in my exponent, and if I want to get rid of the fraction, I can. What I could write this as is 1/6, sorry, 1/6 to the -3x plus 2 power. Getting rid of the negative from both of the terms in the exponent, or factoring out that negative. And now I can apply the -1 to the 1/6. So this would be 6 to the 3x plus 2 power. Remember, that negative would take the reciprocal of the fraction, which would be 6/1. Now I can probably see that, okay, if I have a base of 6 here, on the other side of the equation, I can turn 36 into a power of 6. This would be 6 squared, the x plus 1 power. So 6 to the 3x plus 2 power is equal to 6. I'm going to combine my exponents there to get 2x plus 2 power. So then, if the bases are the same, and the exponent, then the exponents must be equal here. So 3x plus 2 is equal to 2x plus 2. Now, if I simplify this, I would come up with x equals 0. Now, let's check this to make sure that this is accurate. So I would have 1/6 to the -3 times 0 would just eliminate. So 1/6 to the -2 power, which is 36. If I had 36 to the 0 plus 1 power, that would be 36 to the first power. So they would both be equivalent. So the uniqueness property allows us to solve for variables and exponents if we can get the equation to have the same base on both sides. Let's take a look at D. D is going to kind of work in the same manner here, but what we're seeing is we're seeing Euler's number. So we can still solve for D. Remember, Euler's number is approximately 2.718, and then it continues on and on. But it is a base, okay? So E is a number. It represents a number. So we're still going to try to get the same base on both sides. Now, let's go ahead and let's try to simplify this expression using our properties of exponents. Remember that if you are on the left side of the equation, multiplying two bases, we can add their exponents. So this would be e to the x plus 2 power. If we are dividing two bases that are the same on the right side of the equation, we can subtract their exponents. So this would be e to the 4 minus x plus 1 power. If I simplify this, this is e to the x plus 2 equal to e to the 4 minus 1 would be 3. So 3 minus x power. Now I can simplify this expression again because I have two bases that are the same. So their exponents must be the same. So x plus 2 is equal to 3 minus x. Now I can solve this expression by adding x to both sides, subtracting 2 from both sides, and then dividing by 2. So I would get 1/2. So here, if I want to simplify, or sorry, to check my answer, I can do e to the 1/2 power times e squared, and this is going to give me an irrational number, and then I'm going to compare that to e to the 4th power divided by e to the 1/2 plus 1, or 3/2 power, and see that they give me the same decimal approximation. So I have the solution. So What we did in D was we just simplified the expression by combining bases on either side of the equation to get a single base, and then we were able to use the uniqueness property. And this is a method for solving exponential equations. It's not the only method, but this is the one that we have the skills to execute for now. So this looks like a good place to stop. Thank you guys for tuning in, and I'll see you soon.